Esta es más alta, Alex.
Más alta, más esta. Sí, però és igual que aquella. I si posem... Mirem aquesta aquí lliure. Si nos están viendo por la cámara, que es muy divertido.
Ella está yendo abajo.
Ay, son ideas.
Demanan algo. Sí, y ahora has de conectar-la, ¿eh? Y el cable está al otro lado, ¿eh? Per això.
No, però posarem zoom.
No s'ha de connectar per cable? No, eh?
L'única cosa és que per gravar, sí, ho podem fer. Com ahir vam fer, sí. ¿De verbo? Sí, pot, però puedes.
Te quedas hoy después de la sesión de tarde. Bueno, aquí a último ya acabamos la clase. Vamos a poner a nuestros proyectos.
Ah, pues me queda un rato. Un ratito.
Tranquilo. Si podías, no.
Japan. Oh, okay. Okay, so in anime.
Mira. Sí, aquí
Very, very famous town. What's the name?
¿Millor? Me vas a corrido, ¿eh? Ara corrents, eh?
Vale.
Si me ves alçada, potser se li pot posar una.
This number 8 was built.
La taxa.
Són 8?
Treu dos punts. La taxa directament a sota.
Almost as old as me. A ver. Están las fotos. Entra con la buena.
Ara me l'emporto jo.
Vale, la foto
Yo no, de temperatura.
Deixa'm un temps, perquè normalment quan t'assentes, però sí, una mica millor. Una vez es la pantalla. Better now they turn down the AC.
Yeah.
We will just have this. ¿Cómo per gravar? Comencem aquí, no?
The shirt, like buttons.
Ah, no, te pots posar tot el host i després aquí li dones a gravar i simplement te demana permís i dones que sí, saps?
I el so? Millor que no, no?
Sí, això. Sí. Li farem un host perquè pugui compartir pantalla.
Esteu gravant? Ah, no,
No, està molt bé.
What were you going to celebrate?
La vam gravar, oi? La seva
Sí, i va sortir que es pujava el núvol.
Notice?
Можливо, 100%.
Cigarette, but
Potser no cal que es vegi la tele allí, si tot allà estàs compartint pantalla. Vols que te fiqui més cable a tu la càmera?
never tried. Only on friends. For your defense. Okay. I think he did not like
Així? La càmera?
¿Cómo están las aulas de la uni?
Debe fer justo.
Això és que m'ha no?
S'ha aturat la gravació d'abans. Igual Ara què? Has d'anar com els participants. Vale,
Pero yo soy...
Recording in progress.
Vale, però crec que això és el que va passar. Però ho saben, o sigui que la pugin després i ja està. T'estàs escoltant?
Sí, ja mandamos.
I think now it's working everything or not. So someone in the chat can confirm that is working the voice, please.
Yes, it is.
Someone in the chat. Yes. Okay. Thank you. Okay. Okay. Let's try third iteration. Let's try if now it's working a little better. So you can see it well. People can see it well online also. Okay. So fourth session of theoretical part, as you know, as I was saying, the first in the morning are more theoretical. Now maybe someone has the microphone on. Okay, so more theoretical. Then after the coffee, there is someone with maybe I can who can silence the others. Maybe us. So So this is the problem. Now it's okay, the sound? Okay, great. Yes, the notes are uploaded, is it?
Yeah, there are with the other session.
Yes, they are uploaded. The lectures 3 and 4, they are uploaded, so you can download it from the website. Okay, so the first two sessions, so in the morning, as I was saying, we are typically doing more theoretical. Here, then we do a more practical machine learning, and then we do practice there. So we have done this one, what was constraint optimization. Then we have done first introduction to machine learning. And yesterday in the afternoon with Tony, we have done some practice in Python yesterday. Today, we have done constraint optimization in the morning. now we are here, the second part of the machine learning, and in the afternoon we will have another practical session with Tony also. Today it's going to be classification example. Okay, so let's just recall a little what we have been doing yesterday. Remember that we had some definitions of artificial intelligence, machine learning, representation, and deep learning. This was what we have learned, that the difference between artificial intelligence and machine learning, representation learning. Okay, remember that the bases are very important. I think someone else has the microphone.
No.
Mute. Mute.
If you are the host, you can mute.
Ask all to mute, no, mute all. But maybe also I will ask CIMNE, and I don't want. Okay, let's continue. So machine learning, yes, representation learning and deep learning. Okay, and we have seen some examples. Yesterday we have seen also the difference between supervised and unsupervised. As you remember, supervised was just the features and outputs, and unsupervised was just features. Okay, we have seen the linear predictors is a case of representation. We also have polynomial predictors. Why not? Polynomial predictors. And then we have seen the difference between them of decomposition and deep learning also as an example. Okay, we have seen why the representation is very important. And we have seen also how deep learning can start constructing and building new features, very, very, very difficult and sophisticated features that you also use some parameters to build. And at the end, you can classify different problems. We had done the first example, the linear regression example. You remember? So this was the example with the solution of the problem. We did also with the L1 norm of the problem. So L2 norm, L1 norm. We have seen that we have to solve a linear programming problem. We have done also the L infinity norm, which is the Chebyshev approximation. And we have seen that also is the same as an optimization problem, linear programming. And yesterday in the practice we solved it with some optimizers. And then we understood why you have different solutions once we have absolute values or L2 norm or L infinity norm. Depending on which norm we use, we have different solutions. We knew that we can provide other penalization norms, and people are using them. And then we have seen what is the difference between optimization and machine learning, which usually optimization we use it for machine learning, but what is the difference? We have seen that it's arbitrary to use polynomials, and it's also arbitrary to say that we are going to use linear, maybe quadratic, cubic. The capacity, we were saying which is the optimal capacity. We should have order 3, order 5, order 10. And then we realized that in machine learning, what we do is to divide our data in 80% is train and 20% more or less is test sometimes. And what we want to do in the optimization is minimize the mean square error, but the real objective of machine learning is not to minimize the mean square error, is to minimize the test error, because we want to predict. This is the differences. If we want to predict, what we want is to make, if new data is coming, that we will be sure that we will have a very small error. Okay, so this idea, we have seen that if we increase a lot the capacity, we will not minimize also the test. We will minimize the train. We will be perfect for this problem, but not for the test. So there is an optimal capacity we have to choose in order to minimize the train, but also minimize the test. What we want to minimize is the test. Okay. So if we have too much capacity, it's overfitting. If we have too less capacity, it's underfitting. Okay. And we have seen this, how this curve is going up when we add capacity, we have more polynomials. And then we realized that there is an optimal capacity. And we understood also in terms of linear algebra and an optimization problem, we have seen that at least a very toy example of least square problem can be understood as underfitting of overfitting, depending on how much data you have in terms of capacity, in terms of theta. So if you have few data, few thetas, but a lot of data, then you're underfitting. But if you have the contrary, few data in comparison with the capacity you will have overfitting, because it's like you having just few equations and too much unknowns. And probably when you will solve this equation, this matrix will be not invertible, and you have plenty of solutions. Okay. But then, and this is what how we finished. We were saying that, okay, we have problem. We want capacity because we want in somehow to minimize the error. We want to be able to adapt in different regions. In general, capacity should be okay. But let's say, okay, if it's too much capacity, we are going to overfit. Let's try to say we are not going to have all possible solutions. Let's say from all possible solutions we will have, let's take the ones that will have less norm of theta. For example, this is what is called prior information. So it's not any theta, it's not any unknown, are the unknowns that has small values of theta. Okay, this way we regularize the problem. We give more information to the problem, so we are not going to have infinity solutions. We're going to make it better well posed. Okay, and this is what is the regularization, L2 regularization. Yesterday we spoke about Tikhonov regularization. Okay, and in numerics we can also understand this as just adding a matrix lambda I as a mass matrix, for example, that we use many times in finite elements, that stabilize your system. And when you do the inverse, then you have a unique solution. This matrix becomes full rank. Okay, so we have understood that in fact, instead of using capacity as which is the best capacity, we are going to use, and we see it also in the practice, we're going to use a lot of capacity. And then we will take this lambda in a way that we will minimize also the test error. Okay, so lambda plays the same role as the capacity. Okay, so we will have the good things, high capacity, we can adapt on different parts, and at the same time we will have a small test error. That is what we want to minimize, not the train error. Okay, okay, so this is yesterday. Now let's continue. Yesterday, in fact, was an introduction, and we start with very simple example with linear regression and polynomial regression. And it is in fact already a supervised learning example. Okay, so supervised learning is the data you have are features and outputs. An example was, imagine the place and the day we are and the time, which is the temperature. You have some data of this, and then what you want to do is, if again someone tell me this is the day, this is the place, and this is the time, what is the temperature, you want to predict this and do it with a small error. So what you do is, with the data you have, you want to minimize. You minimize mean square error, and remember the matrix X was a matrix with all the data here, and if you use polynomial regression, you add columns with polynomials, and you evaluate all the polynomials here. Okay. If you have more than one variable, x1 and x2, you will have also larger capacity. The more is into the right horizontal, you have more capacity. Okay. But it's also arbitrary again. Why polynomials, as we do in machine learning, in finite elements? What is why we want to represent our data, for example, depending on the temperature, depending on the square of the time or the day? Does it make sense? has some physical meaning. So that sometimes we propose, but we don't know exactly if it makes sense or not. So we have to understand that what we have been doing yesterday in the practical part was adding these columns that are difficult to understand why the output depends quadratically of the time, for example. Why not cosinus, sinus, exponentials? Okay. So I was going very fast about with regularization. So I think, and this is very, very important in machine learning. Let's speak a little more of regularization and different examples. So yesterday, we were proposing L2 norm regularization. So what is called Tikhonov or right regularization. Tikhonov regularization. Okay. We can understand as a prior knowledge of theta. So theta is not anyone, but it's small value of it. We can interpret also this in physical meanings. Sometimes, for example, imagine you have a problem in elasticity, as I was saying yesterday. Imagine your matrix is not invertible because you don't fix the boundary conditions. You will not be able to solve the equation. So this is not going to be invertible. But if you penalize, if you say that the displacements cannot be infinity, because if it's infinity, you're not going to minimize, then you will have a solution. Before you didn't have a solution. Now you penalize the displacements. You don't like that the displacements are infinity. Then you have a solution. Well-posed solution. You regularize the problem. Here we can see it similarly. Instead of thinking that the problem was bad posed in the sense of the matrix, and then we minimize the displacements. Also, here we minimize the unknowns, which instead of the displacements or temperature or finite elements and P's, here are just the variables we want to compute. Okay. But this is also arbitrary. Why L2 norm? Someone can ask why we don't use L1 norm or L infinity or with another mass, another definite positive norm. And in fact, we can, yes.
But this penalization term is not a Lagrange multiplier, right?
Okay, good question. No, it's not a Lagrange multiplier, even if we put lambda also. But if you add this norm as a constraint and you ask to be smaller or equal than 1, okay, so you think you want to minimize the least square problem, but with a certain norm not bigger than this value, then this exact lambda can be interpreted as a Lagrange multiplier, as a constraint. So how large you put this lambda, in fact, measures how important is this norm in the cost, as we have seen in the previous class, exactly. So yes, so that's why people put lambda here. But the thing is, in machine learning, constraints are optimizers that tries to solve constraints optimization problem are sometimes very expensive. So the philosophy of machine learning is to go fast, not doing inversives, and not tackling with constraints sometimes. So you just penalize and you solve a constraint optimization problem. So, but this is why the name is lambda also, because it comes from this idea. Yes. Why we are not using inversives? I don't know. Yesterday I was speaking with Tony, and I think there is an example now. How many design variables was this example? You remember the
10 billion parameters.
10 billion parameters. The last example of in machine learning, in deep learning. So can we do an inverse of that? Can we even think of constraints of that? So what we want to do is to go fast, very fast, and doing gradient methods, as we have seen, or stochastic gradient methods. Okay, so you go fast with a lot of data, and you just do multiplications and addition of vectors. Even if you don't want to do matrices, vector multiplications. Okay. Okay, but this regularization is very important. So another option is, instead of saying that you can analyze then L square norm, you can say no. Why not the L1 norm? What is happening if we penalize the L1 norm? Who can help me on that? Who remembers what is the effect of penalizing L1 norm?
What happens with you if you do the ridge problem is that your coefficients never get to 0. They get to a value similar to 0, but with lasso, they get to 0. And this allows you to erase that variables from the problem.
Exactly. And remember, this is what we have seen yesterday about L1 norm. Why was it important, the L1 norm? Because the solutions, most of them maybe will be large, but some of them will be large, but most of them will be 0. So you can do the same effect instead of for the errors that we have done yesterday for the design variable. So that your design variable, you will have from all that you will have, some of them will be large, but most of them will be 0. And then you can represent your solution with just few variables. Okay. So it's a way of having solutions, very, very sparse solutions. Okay. So your solution is just with some theta's. Some of them large and some of them 0. In fact, this is called the lasso problem. So the regularization with L1 norm. And let's try to understand what does it mean. Imagine you want to solve a problem, a least square problem, that you want the cardinality of theta is smaller than 10, for example. Imagine you have theta 100 variables, and you want that the cardinality, which means that 90 numbers are 0 and the other 10 are different from 0. You ask for a discrete number of variables, and this is very difficult to solve. It's the L0 norm, and people don't solve this problem. So you ask for many of them 0 and some of them not 0. You ask the cardinality. So from 100 numbers, 98, 0, and 2 different from 0. This condition is discrete. You cannot impose it in continuous optimization. Okay. So the lasso problem is the best way to approximate this problem. This is a very interesting problem because from all, you don't have to store 1 billion variables. You will only want to store 10%. This is very interesting for machine learning, but the best way to do it is with the lasso approximation. So instead of the L0 norm, you use the L1 norm, which is the absolute value. Okay. See here an example of the solution. So you can see the error is increasing when you ask the cardinality to be very small. So the cardinality is small, for example, you want just one number. Then you have this value of a lot of error. You want 2 numbers. So the cardinality 2 here. So this is the value. Here, cardinality 3, 4. You see? So when you want to solve your problem with more thetas, you allow, instead of 10%, you allow 20%, 30%, or 80%. Of course, you will have less error. Okay, that is why you are going to the left. And this is the continuous line. Okay, the dashed line is the L0 norm, the L1 norm. No, sorry, it's the contrary. This one is the L1 norm, and this one is the L0. So it's happening exactly the same, but it's approximating the solution. So it's not the best. It's not the L0 norm, but it's very, very similar to it. It's how you will solve the problem. And again, what is the problem of the L1 norm? Who remembers what is the problem with the L1 norm? Not differentiable. Thanks. So we need to do some tricks. As yesterday you have seen, we had some variables. So you have solved the problem. There are people who are also regularizing this problem, which is called the Muroyo-Shida regularization. You use proximal algorithms, some algorithms you can use very fast for solving this problem. Okay, but this is another way of regularizing. one way was saying it's going to be small. This lambda we have seen, now it's another way. Here I forgot also to put lambda. Okay, let's try to understand another regularization. Now, I'm going to say that I'm not going to regularize the problem asking to have a small norm, but asking to have a small norm of the gradient. So I don't want to have oscillations. You know, the gradient is very high here because in a few space, you will have large changes. So here the gradient is very large. And if you do the integral of the gradient, it's going to be a very large number. So imagine you have a noisy data. And you ask, I want a data that is very similar to this one, but has no infinity norm of the gradient, that you can control this norm. You see this data like this, and you say, I don't like this. You give prior information. Now theta is the displacement, the unknowns at each point. So you add another regularization. So you give prior information. Always, if you are clever on the way of giving prior information, you will solve better the problem. But then you have to choose the good regularization. So in this case, you will find theta very similar to y, but with bounded norm of the gradient. Okay. And you can see this as a filtering, in fact. Yes, Ricardo.
It is a stupid question, but how is this different from a penalization in the sense? So you can choose lambda to be either a parameter or an unknown.
Yes, it's a penalization. It's a penalization. A lambda, you have to choose it. Yes. People in machine learning typically, as he was asking, they don't use lambda as a Lagrange multiplier to be computed and adding more variables and having constraint optimization. You just penalize and go fast. Let's try to understand this example, because this example is also very used in PDEs. We can try to see how it's related with PDEs. Let's see it. So the problem is, I have some data or some function that I want to be very close to it in L2 norm, but also that has bounded variable, bounded value of the gradient of theta. So y has very large. This number is very large for y, infinity. But you want one that has less value. This very similar to this one, but with this. Okay. Let's do the derivative. Kato derivative. This is a function. It's not anymore a vector. Okay. Probably you have used this many times in your PD's problems. So you derive here. You have to do 2 times I minus theta times the direction. This is the direction, feasible direction, or perturbation, or compatible displacements, as you prefer. Here you just see it as a derivative, directional derivative. And then you do the same for the gradient. So it's E squared, gradient of theta, gradient of V. And this is an unconstrained optimization problem. So you are going to make it equal to 0. As we were doing the first day, the gradient equal to 0 is a minimization problem. For every because the derivative and optimization, what you want is for any direction. This is the weak form, as we see many times, and V takes the place of the test functions, PDs. Okay. So theta is your unknown. Then you put theta in the left-hand side, and you put y in the right-hand side. And then this is the weak form. You can integrate by parts, or disintegrate by parts, and you will have a strong form. And this problem is a PDE, but maybe you have different PDEs. This is typical Laplacian. So this problem is theta, you see, very similar to y, but adding something else, the Laplacian. This is why we say that this is smoothing. You know that the Laplacian gives it a smoothness. And this epsilon square was penalizing the norm of theta. So, in fact, some regularizations come as differential operators, as Laplacian. And now you can use your favorite discrete problem, okay? Discrete technique, like finite elements or whatever, for example, and you will get the mass matrix plus E squared kappa is the stiffness matrix, and you solve this problem. I put epsilon also in this color because this is the lambda we were using, and it now makes sense in the terms of length scale. So epsilon is the length scale you want to filter, which is the same as lambda in the problem before. So depending on what you have here, lambda can have some interpretation. It's the dual function of this constraint. So in this problem, regularizing like this is like smoothing or like filtering. Okay, so it's another option of regularization. Another option is the total variation. The total variation is similar, but instead of asking to be the L2 norm of the gradient, is the absolute value of the gradient. And the idea is, who could tell me what does the total variation means? This is the L1 norm. What will be the effect of this? L1 norm of the gradient, penalizing this.
That the data cannot vary much. They have a certain range in which they can vary.
Yes.
But they can capture the discontinuities.
So
if you use the same regulation than before, the discontinuity would be smooth. And in this case, as this is an L1 norm, you can have like very departure on one point that is the discontinuity, so you are not regularizing the function at a strong discontinuity.
So remember, L1 norm means most of them 0 and some of them large. So the gradient will be large, some of them, but most of them will be 0. So here we will make them 0 because most of them that are very large, in fact, they will make it 0. And we leave some of them large. This gradient is very large. So it's like a sparse representation of the gradient. We want that the gradient is in some places large, but in most of them 0. And this is very useful, of course. This is called denoising. So you know that your information has some steps. You know, for example, it happens in images. In images, you know that you have discontinuities. You have a pixel here and a pixel here, and you know that, for example, you know that an image of a person will have a boundary. Of course, there is a discontinuity, but also will be noise there because you take a picture and it's not perfect. So what you want is to reconstruct the function considering this boundary, but all the noise, all the gradient, remove it and put it to 0. And this is what is happening, for example, in many images that are a little not with noise, and images that has some resolution, a very not a good resolution. Now with this denoising, you have better resolution. You improve the solution because you give prior information. You knew that your function has discontinuities, but has no this noise. You had this information. Why you don't use it? And you add it as a regularization term. Okay. So this is why it's called prior information. Also, okay. On Thursday morning, we'll have a session understanding priors more in terms of statistics and understanding also this regularization in terms more in statistics. Okay. But this is just very much used on not only in signal processing, but in other cases. Okay. Variables are very useful, and I put just some of them that can be understood as total variations, as PDEs, okay? But you can put anything you want. Imagine you know more information. Imagine you know that your data that you want to approximate is, for example, a combination of something, or comes from, or you already have other data that you know that it's perfect, or anything this information you know, put it there in a way that you can minimize well, and it's clever, of course, but use it. Then you will regularize your solution. These people in optimization typically say that if you have solutions that you know one is better than each other and both has the same cost functions, but you say that one has the same is better than the other, it means that your model is not good. You have to change your model. You have to add something in the cost. Okay. So once you want to solve so many machine learning problems, if you don't like some kind of solution, yes, questions about this idea? Organization? Chat? Maybe in the chat. No, okay. Okay. Just to, if some of you are interested on how to solve this problem, okay. Again, we have the same problem. We have absolute values. It's not differentiable. So there are ways to solve this problem. Instead of using prox or gradient method, you use proximal gradient method, it's called. You add some terms. I have no time to explain it, but there are cheap ways to deal with absolute values. Okay, it's just adding another quadratic term, and then with some smoothing parameter, and then you converge, and you can prove that you can converge very fast. So nowadays, absolute values are something that in optimization we like, because it's not a big deal. Okay. Okay. This will be so much connected with the problem we are going to work on Thursday, which is model order reductions, or problems that you want to have the data to be very also sparse. You want to represent your data very sparse way. So this is also, we will see it on Thursday, but you can have your data, instead of doing a linear regression, you want the data to be sparse. And we will use also this kind of L1. Okay. Okay. So this was classification, the first example, or the typical regression, polynomial and linear regression. Okay. And this helped us to fit some curves, and we knew, and we said that y was can be any number. Okay, can be from minus infinity to infinity. Now in the logistics regression is what we use for classification. Now you have data, you have supervised data. So now x can be any number, but y should be between 0 and 1. For example, the tumor size. Imagine you have the tumor, a tumor. I will put it in blue. Okay, that is from 0 to infinity, the data you have. And now imagine you get some data and you knew, or that from other ways, you knew that some of them is 1 and some of them is 0. It means that some of them are not malignant and some of them are benign. So some of them are good and some of them are not, depending on the tumor size. And you want to classify. So how do you classify? You say, wait, let me pass a step function here in a way that all the points that are less than this number, we will say that it's okay, it's benign. And if not, it's malignant. Okay, so okay, this is how you classify one variable x, one output between 0 and 1. More or less easy. You have to fix where to put it. You have to find this theta 0 in a way that you minimize this error. You can move this line to left to the right. Okay. So this is an example of classification. But things become more difficult when you move from one variable to two variables, for example. Now, data maybe tumor size and age. You want to represent your data with more features. Remember, X are features. So you say when X is small, for example, all of them are benign. And if tumor size is large and the age is large, then it's malignant. This is data you have, and you want to pass a line, classify. How? Why you want to classify? Because what your objective is. If someone tell me what is the tumor size, again, and tell me that which is the age, I put a point here, and directly I can say if it's malignant or not, or directly I can say if it's benign or not. You want to predict this. So the machine learning idea is to learn, to have like a machine that has learned how, if you give me the input, I will give you the output. Fast, very fast. Okay. This is in 2D, but features can be 1,000. Imagine. Okay. So one thing is the number of features. The other thing is how are we going to use, which hypothesis function we are going to use, which is the hypothesis space. Again, in linear regression, we were using polynomials before, but it's arbitrary. We can use other things. Here we are going to use also polynomials at the beginning. Okay. And you will see, as I was saying in deep learning, this is very important. How you will use this will change a lot of things. This is the f theta that I was explaining last time. Let's go there. It was here. Just to relate things. Remember, for deep learning, you have to choose two things. What is f and what is theta? So the composition of these things will give you your solution. So theta, you will have it from optimization, but f is something you will propose. Now we propose, instead of f, I call it h, because it's called the hypothesis function, and we propose a linear or polynomial. Okay. This is important because sometimes it brings a confusion on the first time you see it, is that you say, wait, is this linear or is it not linear? So in theta is linear, but in x, maybe it can be quadratic, cubic, or whatever. So you see, we don't put here theta squared. We just put theta, which are the weights, are also called the weights, and the basis functions are x. Someone can ask to put, someone could ask, why we just put linear in theta? At the moment, we have seen always linear in theta. Okay, and why? The thing is, we have two things. The thing is theta, if it's linear or not, and x, if it's going to take into account x squared, cosinus of x. So x brings everything depending on x. So x squared, cosinus of x, exponentials, whatever. And theta is a weight of this function. So it's a way of representing a linear combination of your bases. But the bases can be very, very, very sophisticated. And this is also linearity. There are many neural networks that they don't propose these linear aspects. And we will see in neural networks tomorrow, and also when we code it also tomorrow, that we have linearity, but then we have nonlinearity, and the combination of linearity and nonlinearity brings nonlinear things, very nonlinear things. And this brings to very sophisticated functions or features that are going to represent our data. Okay. Okay. So now, what is the thing in classification? The difference in classification. The difference in classification is that our output want to be or 0 or 1. Before can be any number. So we didn't use anything more than this. Now we use a Heaviside function, a thresholding, that I will put it here. So that will try to be h theta of x. So when is less than this value, it's going to be 0. And when it's higher than this value, it's going to be 1. Okay, thresholding of Heaviside function. This is discontinuous. Okay. However, we like gradients. We want to minimize many variables. We cannot use other kind of optimization algorithms, evolutionary algorithms, this kind of things. We cannot use it. We need to use gradient, stochastic gradient. So we need differentiability. So instead of having this step function, we will regularize it and we will provide what is called the CIMNE function, very famous. Probably you have heard of it many times, or logistic function. It's called logistic function or CIMNE function because it comes from what is called logistic regression or classification. Okay. What is this? This is very easy to understand. It's just this function here. 1 divided 1 plus exponential of minus z, and is a function that is smooth, that is 1 for large values and 0 for negative values. Okay. And of course, you can just change this, the point of 0, just doing a shifting of z. Okay, so you can move this value. So this is why, and this is important in machine learning, you remember that x has columns, x squared, x1, x2, x squared, and we have a column of ones. Why? Because we want theta 0 to exist also, so the affine function also to use it, and this is important. Why? Because then we can move our logistic function. This classification, we will be able to move the line. Okay. This line, you should imagine in 2D as this step here. You have to imagine this line as a step function. Here 1, here 0. So something like a step, but in 2D. Okay. Then you can move where is the step. Okay. Okay. Now, interpretation of G, of this CIMNE function. Questions about this CIMNE function? Or yes.
When we make it a continuous function, then how we say like the value may be very near or far, like a mid value, how we make it either 1 or 0?
Yes. You can say if it's below 0.5, it's 1, and if it's larger than 0.5, for example, it's 1 at the end, thresholding, and you can do it. But you can also, and this is what we are going to see now, you can interpret it in probabilities also. But yes, you smooth it, and you can make it more step with a parameter also if you want, and you can be more sure, more robust that your solution is fine. You will have a less transition. Okay. More questions? No? Okay. So now we have our hypothesis function and we have our activation function, or sigmoid function or logistic function. We have both things. Now, what is the meaning of this? Typically, if y is 1, so for example malignant, and the input was x, g of x theta means how much or how likely is that your tumor is malignant. So for example, if it's 1, it's 100% sure. If it's 98, so here, you can see it as a probability. You can say 98% of probability that your tumor is malignant. So this grace, even if we think as a smoothing of the function, we can see it as a probability also of the solution. So sometimes, or some other times, it's very useful because you don't want to answer in terms of sure or not sure, just probabilities. Okay. So more mathematically, we say that for some x1, if the solution is 0.7, there is 70% chance of tumor being malignant. Okay. So the probability, this kind of probabilities you have here 0.7 and 0.3. Okay. So the contrary is also happening. So this is, I don't know if you are used to this notation, but this means, in terms of probability, it means that g of our hypothesis function. So we have solved our theta. Someone asked us a new x. Someone provide us new data. Then we have the theta because we have optimized the problem. We multiply h and then we pass g. Then we say that the probability that y, so that to be malignant, y is equal to 1 when the variable is this x. So when we have this tumor size for these values of theta is something. You read it like this, okay? These formulas are read it like this. I say it again. The probability of being malignant, so y equal to 1 when this line is when our data, which is typically called random variable, is x. X means, for example, this tumor size and this age, with or given theta, with this value, is something. Okay, this is the way we read these probabilities. We'll see that they are very useful in because we can understand this regularization. We will understand also. Yes.
But this doesn't give you any information about how confident you are in your predictions, right?
No. No.
So this is just, okay, my model tells this, but I may be wrong.
Yes. Right. Yes. To have confidence in your prediction, you use other estimators. And the contrary. So as you know, the probability is 1 minus g of h of theta times x. So you just do 1 minus p I equal to 1 is the same for p of y equals to 0. X takes this x given theta is 0.3. So this is important to start trying to read these things because we will use it on Thursday, and we will use it maybe tomorrow to understand what is the maximum likelihood estimators, what are the maximum posterior estimators, and these things. Okay. So now we have the linear combination, and we have the g function, the sequence function. Typically, it's going to be 1 when theta times x is bigger than 0, and 0 when it's less than 0. So in classification, what we say is that this line, precisely the one that divides both, is smooth now, but for example, the number 0.5 is what we call this decision boundary. We call it decision boundary, is the boundary, okay? To say if it's one or the other. Okay, so what is the difference now from logistic regression, linear regression, polynomial linear regression with logistic regression? One was for data, general data, and the other one is for classification. And the other difference, and very important difference, is the cost function. Now the cost function is not going to be anymore the L2 norm of the error. Okay, it's not going to be this anymore. Why is not going to be this anymore? Because now what you want to do is, you know, information about y is or 0 or 1. Your data, your output is or 0 or 1. Okay, so you want to be, you know that it's 0 or 1. So you want to make 0 the error in that at that numbers, not at any numbers, at that values. You take profit of this. Okay. And what is the cost function? It's called the negative log likelihood. Okay. We will see how we can interpret it in terms of probabilities also. Also, it's called cross entropy sometimes. Okay. And has this form. So I put it here, and then we are going to understand it. So is the addition of all the data, and for each value of the data is 1 minus y. So y can be 0 or 1. As you know, this is the data. Data is or 0 or 1 times minus the log of 1 minus the activation function or sigmoid function with the hypothesis function, composed with the hypothesis function. Okay, plus y minus the log of composition of sigmoid function with the hypothesis function. Okay, let's see how it works. Imagine that y is 0. Let's take one data. For example, y is 0. Someone goes to the doctor and say, okay, this tumor is benign. Y is equal to 0. Then this term cancels. You don't have this term here anymore in the cost. However, here it's 0. You have all the time this part of the cost. Okay, and look what is happening. You want to predict that y is equal to 1. So what you want is that g is very similar to 1. Okay, you want that g here, g of theta x here is equal to 1. This is what you want. And g theta of x here is equal to 0. This is what you want. So what you want is that g is very similar to 1. This you can see it as an error. If it's not 1, of course g will be always smaller than 1. Remember that the sigmoid function has this property, will be always smaller than 1. So you will have no problems here with the log. So this number here, if it's going to 0, this log, what is happening with the log of 0? Log of 0 times plus infinity. Okay. And so you penalize a lot if g that you ask to be 0, y you ask to be 0, if you have g equal to 1. Okay. So you want the g. I think I was saying in the contrary. You want the g to be 0 because y is we say that is 0. Okay. You are here. Here in this point, and you have y equal to 0. I should put it in green. Sorry. This point here. Okay. So g you want to be 0. But if you go to 1, this is going to be 0, and the log of this will go to infinity. So you are trying to avoid the most that g is going to 1 when you want that g, in fact, is going to 0. You penalize the contrary. You see? This is the idea. In the other case, let's do the other case to repeat it and understand it better. The other case was, imagine y is equal to 1. If y is equal to 1, the doctor goes to the hospital, the doctor says, yes, this tumor with this tumor size, has this age, the patient is malignant. We have these 3 data.
Then the other part is 0.
Then the other part is 0. We don't care. But now you have to focus on here. So here we see that y is going to take 1, so it's a 1. And then look, if j, so now we are going to solve the problem. We're going to find the theta such that we minimize this. We want to minimize this. So if the theta with this x, theta that we have to find, gives a value that after g is very close to 0, the contrary that you want, this log tells you, wait, 0 minus infinity plus times minus is plus infinity. So you dislike very much when you have a data that is 1 and you get a prediction that is 0. I see your faces as should I do it again? This is important, very important. Negative log likelihood. Question, please.
You explained it quite well. For sure.
Yes, Ricardo.
Would this behave correctly when you define a precision? Meaning, if you have, let's say that you have the sigmoid function, then it will be almost 1, but not quite. It will not overflow.
Yes.
This happens sometimes. So you can just avoid it by telling a condition. So if it's really close to 1, don't take the logarithm, just take a really negative number.
So you threshold.
Yeah. Yes, it happens. Okay, so I think, and this you do it for each point. So you have to imagine, and this is important, that you are trying to minimize the combination of data, a lot of data, okay, a lot of terms, and each term all of the theta will be in all the terms, okay, and what you are going to say is, wait, if in this data y is equal to 1, I will penalize a lot when you predict that it's going to be 0 with a log. And in the data which we have 0, we are going to penalize a lot if we predict equal to 1. Okay? This is the idea of negative log likelihood, and this is the idea of cross entropy. Okay? Things of this, we can plot it here. So we have here value 0, value 1, and then if you're here, if you predict a value equal to 1, I will penalize a lot. See? If the data is in 1, I will penalize a lot once it's very small. So when we go to 0. Okay. So this is the idea of the log likelihood. Another important part that is useful is that it's differentiable. Okay. Okay. Property of the sigma function. The sigma function has this property. So this is the definition, and if we take the gradient of it, you can write it as a combination of the function and 1 minus the function. So if you do the derivative here, then if you write this as 1 minus 1 plus e minus z, and you add 1 minus 1 minus z, okay. This cancels with this. Square. Is something wrong or not? A minus. The derivative of this is 1 divided by this. The derivative of this But where is the minus? Maybe, is there a minus here?
Because the derivative of the quotient got a minus, and
Yes.
e to the minus z, another minus.
Yes. Exactly, yes. So the derivative of this is minus 1 over 1 plus e minus z. But the derivative of down there times minus 1. So minus and minus goes, and then you have the square. Okay, so you have this property, which the derivative of the sigmoid function is the combination of the sigmoid minus 1 minus sigmoid. So, and this is useful because you have already computed. Imagine you have many values of z or theta, and you want to compute the sigmoid of it. You just compute it once. You need it for the cost, but you will need it also for the gradient. So you take profit of this. Okay, and you don't have to do this calculation. There are other functions that are not the sigmoid functions that has not this property, and they are working quite well also. Okay. Now let's compute the gradient of the function. Okay. So the gradient of the function is taking the first term. So let me put it here. Very small. Okay, I think it's going to be fine. Okay, so the derivative of the function. So we have to do the first term, this one, as you can see well. So is minus 1, because this minus here, the log, so you put here 1 divided by this, times the minus of what you have inside, so it's minus this, the derivative of this. But the derivative of this, you know, as we were saying before, is this times 1 minus this. So instead of writing g of prime, I will write g times 1 minus g. Okay, so the derivative of this is going to be g times 1 minus g. Okay, now times what is inside, which is the derivative of h times theta. Why? Because what we have inside is h of theta. We want to do the derivative of with respect to theta. Okay, so this is the derivative of h theta with respect to theta. So it's x because it's linear. Okay, so again, the derivative is 1 minus I. We leave it like this. The log is 1 divided by what we have inside. Then the derivative of what we have inside is the derivative of g with a minus is here, and the derivative of g is g times 1 minus g. Okay, and the derivative of g is the derivative of h, and the derivative of h with respect to theta, because it's linear, is x. Okay, now 1 minus j and 1 minus j is cancelling, and you only have this term here. Okay, this avoids problems, numerical problems, of course. And the other term is very similar. It's y times 1 divided the log. So 1 divided by the function times the derivative of g, which is g times 1 minus g. And then the derivative of g with respect to theta is the same as the derivative of h with respect to theta. So it's x. So now what is cancelling is the other one. This cancels with this. And the log that has many times problems with the derivative, because you have this value that is dividing that can be 0, then it's It's not anymore. Okay, because the sigmoid helps on this term. Okay, but you can do. You know that when, in this case, you have two terms, this term here and this term here. Okay, this term here is just with a j, and this one is 1 minus j, minus g. Okay, g, and this one minus g. So you put it here, 1 minus y. G is this one, minus y times 1 minus g, which is this one. Okay, so yi times g is equal to minus I times g. So you can cancel, and then what you get is y here, and you get g here. Okay, so this is what you have as a gradient. And why is this useful? Why do you think this is useful? Or what do you recall this expression? Does it recall to something? These squares? Yes.
Kind of
Okay.
the sum of errors.
That's it. Let's write it down. Okay. So remember, when we have mean of x theta y here, 1 square with respect to theta, what was the gradient? We call it f0 theta. So the gradient, the derivative of f0 with respect to theta in the direction of theta was 2 times x transpose. Let's do it a little. Distance for x minus 2 times twice x transpose y about theta. Okay, and then and say you can put a 1/2 here, then I will remove the 2, and then you remember that what we have done was say that this was going to be equal to 0, and what we have done is x transpose x times theta is equal to x transpose y. Okay, and we have solved this problem yesterday. Okay, this is what we did, gradient equal to 0. But here, look, the gradient itself is this. Okay, this is the gradient. And this is what we have done yesterday. The solution of this problem, and this was the gradient, you remember? So solving a mean square error, yesterday we said we solve it analytically because we know that doing a linear system of equations we can have the solution. But what we did also is we can do is to use the gradient method. We didn't do it. Today we will do it. But yesterday we didn't do it because we know that has an analytical solution. But we could use the gradient method with a line search. And if we have used the line search and the gradient method, this was the gradient. Okay? We went directly to the optimality conditions. We didn't use a gradient method. So today, the gradient had this form yesterday, but look at here. This is x. This is h of theta, which is x of theta minus y. So it's very similar except of the g. So here, it's very similar. The gradient is very similar to this one, but instead of having linear regression, you pass then an activation function 0 between 0 and 1. And look how it makes sense, because why you want to be or 0 or 1. So this expression recalls so much to the expression of regression or linear polynomial regression. Okay? And probably this is why this is called logistic regression, because it looks like very much as a regression, but you are doing a classification example. You're not doing a regression. Okay. Another question about this is, what are we going to do? Are we going to use a gradient? Or why are we computing the gradient for this example? Why do you think we are computing the gradient? Find the minimum, yes, and how? What are the possibilities to find the minimum of an unconstrained optimization problem? Huh?
Using the gradient method to find the
Gradient method, this is one possibility. Another possibility. Another possibility for finding the minimum of an unconstrained optimization problem. So why didn't we use yesterday a gradient method? Why didn't we use this? This one. Why didn't we use gradient method? Exactly, we have an analytical solution of the problem. We have already solved directly gradient of f of theta equal to 0. We solved this problem, and the gradient was a very simple example, very simple formula. There are algorithms that you can solve analytically, or you can try to, with a fixed point method, you can try to solve this equation, the optimality condition that we have seen in the morning of Monday. But why we here? Can we use this here in this case? Do we have? Now what we want to do is gradient of this equal to 0. This is what we want to do, because this is optimality condition. As Ricardo was saying, here we don't have constraints. It's an unconstrained optimization problem.
Maybe we cannot derivate the x.
This is the derivative, but why we don't?
Be a problem.
It's an implicit equation. It's an implicit equation. Theta is hiding here with g. C is non-linear, g is non-linear. So this is not anymore a linear problem. It's non-linear, so we cannot solve this problem. It's an implicit equation. And theta is there, and you have to find it. So what method did we see yesterday morning that can solve this problem? So if we have an implicit equation, what can we do? Okay, let's go to lecture 1. So for example, what you want to do to have gradient equal to 0, you can linearize and solve a Newton equation. Remember, the Newton was gradient equal to 0. The gradient equal to 0. the gradient equal to 0. You linearize, and then this is an implicit equation. Linearize, you do the inverse, and you solve it. Another possibility is to take the message I want you to take home was gradient method. Okay, difference between gradient and Newton. Who remembers the difference between gradient and Newton? And which one are we going to use here?
We need to invert matrices.
Exactly. We don't invert here. Here we don't invert matrices in gradient. And here we have to invert. Also with preconditioners, we have to invert. What else? So inversion of our matrix. What else? Difference between Newton and gradient. Come on. I know you know.
Not always convergence.
Not always converges the Newton method. Right? Okay. And when we are far, we are not assured that we are going to all the time minimize. Okay. So which method are we going to use? Newton or gradient? For machine learning. Right. Why?
Information of gradient, and we are decreasing the cost in this iteration.
Because of the decreasing, it's not because of the decreasing property. Why are we going to use a gradient and not a Newton?
G also Hessian, we don't need.
We have already said
You don't have a good initial estimation.
one thing exactly. Exactly. Second thing.
Cheaper and faster.
Exactly. Doing an inverse, we don't want to do inverses. We don't want to do inverse of a matrix in machine learning. Very expensive at 20 billions of unknowns. So even if we have logistic regression, but we have the gradient, and then we can derive again, and it's continuous. And we can try to minimize in 8 iterations. We have 2 problems. We need to be very close to the solution, and we have to invert the equation, which is impossible. It's impossible, really, once you want to scale it. Someone, as we were saying yesterday, can propose quasi-Newton methods. What is quasi-Newton methods? Quasi-Newton methods are methods that the Hessian, the derivative, the matrix, are not computed analytically. We approximate it with gradients. You don't want to derive twice. Okay, you just have first derivative, but you don't have second derivative. Are we going to use quasi-Newton methods for machine learning? Right?
Because you don't always have actually you never have the Hessian.
Yes, but you don't have the Hessian, but you can approximate it with, for example, a BFGS of the Hessian. Why we are not going to use it? This?
Because we need to invert.
Exactly. Again, because we need to do an inverse. So we don't want to do inverse. All we have to do is very cheap inverse, or even that we don't have to solve a linear system of equations. Okay. So we are not going to use quasi-Newton. We are not going to use Newton. And preconditioners maybe only if they are analytically or really, really cheap. Okay. So really cheap, and we are going to use gradient methods. Okay. Okay. So the remark here is we are going to use the gradient method, but today I'm not going to explain it, but I don't know. We are going to use it, the stochastic. Maybe. Okay. So the gradient, in fact, is already expensive because the gradient here, you see, look at the gradient. The gradient is the addition of many terms. But you have to do, imagine this is 1 billion. What you can do is, instead of computing the perfect gradient, so you do these differences, then you multiply times x, and then you add all the values. You just do it for the 10% of the values. And this is called a stochastic gradient. So stochastic gradient. We approximate the real gradient. So instead of taking this, we are going to add it to, not to m, to small l and randomly. So L smaller or equal to M. Okay, and this is what really we use in machine learning, stochastic gradient. Why? Because you have many data. This maybe can be 1 billion of numbers, and you are going to just approximate it with 10% of it. And sometimes it brings, yes, 1 second, it brings problems because it's not the perfect gradient. You cannot anymore say that you are going to descend, and you will see it. And probably on Friday, once we are going to use the PINs is physical informed neural networks. We will use the stochastic gradient. You will see that we are not going to descend all the time. We will not have anymore this property. But you can prove that in average, in general, at the end, it can oscillate, but you will convert to a small, you will descend. Okay, so the whole gradient, which is the addition of many terms, so this vector time plus this vector time plus this vector plus this vector, you take only the term 10. For all your data, you just take 10%, for example. How is more or less what it's with
few hundreds.
Few hundred it was, yes.
Usually.
Few hundred is enough to convert. It's not independently of how much data you have. Few hundred is enough. 100 and 200. With this, more or less, you will maybe you will not always convert. Maybe you will increase the cost because you don't have this descending property. But at the end, you will have less value of the cost. Okay. And another advantage of this is it's cheap. So instead of computing 1 billion variables, you are going to compute 100 or 200 variables. And at each step, what you do is you just first step. I use the gradient for the 10%, a random 10%. Then, these 100 values. Then the second step, I'm going to use the 200 variables, different ones. Then the third step, 200 data more of the gradient. So you're not doing a step of the full gradient. You're doing many steps of a partial values of the gradient. But since the data are coming from the same part, the intuition is, since the data is coming from the same structure, you're going to use some of them at the beginning, some of them at the end, and in average, it is going to be okay. Okay. So you want to be fast. So Newton impossible, cos Newton impossible. Even the gradient is very expensive. We don't use the gradient. Okay. And once you have used all your data, it's when we call that it's an epoch. It's called epoch. When you have used all your data. So, for example, if you have 1,000 points, then if you use the first step 100, the second step 100. So in 10 iterations of stochastic gradient, you will say that you have passed an epoch, and you count not iterations. You usually count epochs. This is the language you use for stochastic gradients. Okay, so for logistic regression, we see that it's very similar to regression in general, but a little with the G there. Okay, and then we see that we have to, instead of using a gradient method today, I think we are going to use gradient method and also stochastic. Then you can convert. Okay. Another remark. Regularization. Are we going to use regularization or not? So regularization, also important in this case. We'll have overfitting or not. So just to let you know, I plotted here just lines. But if we take into account quadratics, so these equations here, then it's not going to be any more a line. Probably it's going to be like this, or a quadratic. And if we increase the polynomial, probably what we will have is something like this. And you classify better. Should we increase the degree of the polynomial, the capacity? Well, again, no. Why? Because you will use also the same idea of test and train. Some will be test, some will be train. So here, if you use all the information for the train, probably some points that are not going to be there, we will have a very large error. You will have very large oscillations also. And maybe points that are here will have a very large error. Okay. So again, here you will have to use regularization for the logistic regression. So instead of just solving this logistic problem, what you are going to solve is another problem, which is minimization theta. Now, with this function, plus, and what regularization are we going to use? What regularization are we going to use? Now, for the logistic regression. Okay, what kind of regularization do we have? Let's remember. L2, L1, the gradient for L2 and for L1. This is what we have shown here, but we can have any more barriers. These things. Which one are we going to use? L1. Okay, we can use L1. If we want to be very sparse, a lot of them take the value, so we can see it, this. The problem is that the gradient will have problems with the gradient. We will have constraints. So
L2 because
L2. This does not mean that we cannot use L1. As I was saying, there are, instead of gradient methods, it's called proximal methods that usually are, so just if you are interested with L1 norm, have a look to proximals. They are very famous now and very useful, proximal methods. Okay. And what you do is instead of solving the problem with L1 norm, you alternate directions, in fact. You add another variable and you alternate directions, but this variable is explicit, is analytical, and it's very fast. Okay, so people are using L1 sometimes, but you have to do this instead of gradient. You do what is called proximal gradient. Yes.
But use an L2 norm. Aren't you making less sharp the boundaries?
Yes. More than sharp, less oscillatory, yes.
It's not what you want. So
you want a little because you want to have some richness of the solution. But if you are doing it too much, you will increase again the error of the test. So it's going to be very good because you have a lot of capacity for your data. But then if I give you new data that was not optimized for this data, since this can be oscillate a lot, the error will be very large.
So essentially, you are telling that we need to choose a small lambda.
Yes, the value of lambda should be is usually, for example, I think depending of the value of y and x. So it's not easy. But for example, we have seen lambda in this problem in the gradient is a length scale. You can have some intuition. Here also you can have some intuition, but typically it's very small. For example, our experience is 10 to minus 3, minus 4, minus 5, minus 2.
Yeah. Sorry, this is just for me. Can you scroll up a bit? Imagine that you are trying, sorry, a bit more. When you have, we have the noise, okay, this one. Imagine that what you want is to classify if you are on the top or bottom curve. If you use an L2 approximation, then you have some, I mean, what is happening on the...
You will have this.
On the exam.
You will not have this discrete jump with L2 norm.
Yeah, but then you're introducing them a posteriori. Maybe I got you wrong.
No, just let it say it again. So you say, if you, for example, instead of regularizing with the gradient of the L2 norm, you say the L1 norm of the gradient, you say just the L2 norm of the function. Huh? That what? So this, for example, if you use this, it's true, you will smooth. So before, if you have a lot of information, you will, if you ask lambda to be very large, you will have like a plate at the end. You lose information. It's going to be more smooth in the sense of L2, but it's going to be very flat.
Imagine that they want to use, for example, the sigmoid classification. Okay, then you will have, instead of having this, you will have a regularized shape on those jumps. But then at the very end, you are going to decide, as you said before, that if it is more than 0.5, take something, otherwise something else. So at the very end, it always goes the same way, right?
Yes, you mean at here.
Yes.
Yes. Yes, but this has no dependence on lambda in the sense of regularization. So this is something you have to do. This is true. The lambda, what is helping you is that the change not in this direction, the change in this direction, the curvature, you just smooth it more.
It erases some parameters, like some variables go away. That will help you with inference, knowing how it's.
Yes, this we will see then on Thursday, yes. So regularization is also important, and we use typically L2 norm, okay? We can also use other things like the gradient, but we use L2 norms. As I was saying, people are using L1 norms also for denoising and these kind of things. You can use it, but you have to use proximal gradients instead of gradient methods, okay? But they're very similar in the prox. Prox algorithms are like, prox algorithms are, gradients are explicit. They are called sometimes implicit gradient. So gradient is called explicit gradient, and proximals are called implicit gradients, because it reminds a lot this idea of solving a problem as it happened in the ODEs of people who are doing numerics with time that you do explicitly or you do implicitly. You have to solve a problem. So proximal gradients, you have to solve a small problem, but the good idea is that it's small and very cheap. Okay, so it's tricky. So okay, we are going to use this. So now the gradient of this new function the gradient of this new function is going to be the same plus lambda times theta. Okay. So you have the same kind of regularization as we had for the L2 norm Tikhonov regularization. Okay, so this Tikhonov regularization that usually we see it in ridge regression or in least square problems, you also use it in the logistic regression. Okay. Okay, so I think I finish here. Questions of this part? Yes, Ricardo?
Sorry, question again. I connect to my previous question. Mostly you can make a comment about what to look at. So with what you're showing, let's say you decide a model or a structure of your regressor, and now you talk about how to train it, so how to choose the shape function and eventually how to optimize that. However, the model at the very end may go towards off because it does on the fitting or it does on the feature. That's obvious, you explained it very well. But then, if I was to assess the config circuit, to what I mean, to tell, yeah, how confident I am in the prediction of my model, what would I need to do systematically? I understand you cannot explain all the theory, just
no, yes. This is lecture 2.
Oh, sorry, maybe I skipped.
No, but I think it's nice to see it again because this is not always clear. So what is happening is you're right. With the train, the capacity you minimize, and you say, okay, I do it well. But this is not something that you can say, I am confident that I'm going to predict well. I am optimizing well, but I'm not predicting well. To say that you are going to predict well, you have to take the test, so data that you have not used, and then evaluate the cost function. And if the cost function is large, it means that you are not predicting well. If the cost function is small, it means that you are predicting well. So it's data that you have not been using, but you are going to evaluate.
So let me reformulate my question. Is there a way to equip my classificator or whatever you want to call by a tool that is giving me this? Okay, but in this region I'm not working good, or
so you mean a tool for?
I mean, yeah, just to something that completes my prediction.
This number, this measure, gives you a number, a value of if you're doing it good or not. This mean square error or logistic error or log likelihood of the test.
Okay, right, yeah, I understand.
Yes, with this, and this is what you typically use. You say, I have data. I'm going to do I'm going to optimize. I'm going to make my machine learn. With some data, I'm going to use some data, and the other one I'm not going to use it. And be sure that the machine that I'm going to give it to you has this guarantee that is good, because when I test data that I have not used for optimizing, I have very small values of the error. Then someone say, okay, perfect. If I give you new data, you are going to predict well.
Yeah, but even if you use just the training data,
yes,
your classificator may not classify everything correctly, right?
Yes.
So I was referring mostly to this
okay.
part than to the second.
So you mean more or less which norm do you use, log likelihood, or which functions do we use, or which regularization do we use? So we have like these three tools, which is our hypothesis function, which is our measure, log likelihood, which is our lambda, and which is our regularization. This first, I cannot give like a general answer for your problem. You have to more or less know the data and try to use these tools. Okay. More questions? Okay, if not,
so we have a question.
Yes, sure.
What about, for example, extrapolation? Because sometimes the data is in the borderline. If you want to extrapolate
is maybe something that could be better in order to extrapolate, or it's no way. So the machine learning can only interpolate. Or
I would say if in the cost you don't give information of data that is out of this, so you have used data in this set, and you want to predict data outside of this set, you have no guarantee, or it will be very bad. However, you can use regularization. You can say this data is of the same way of the other one that I have, so I hope they behave similarly. So just with regularization, I would say you could help. Yes. Okay, so to finish, we have seen today in supervised learning what is the linear regression and polynomial regression. Okay. The chat. Does the theta represent weights when we are regularizing without gradients, and represent the output when we are regularizing using gradient derivatives? Does theta represent weights when we are regularizing without gradients, and represents the output? You don't understand the question. I would say yes. Weights are. We can see theta as weights, yes, when we are regularizing without gradients and with gradients also. And they are not the outputs. The outputs are y. So theta are only the design variables. This is what I would say. Okay, so this we have seen different smoothings. Logistic regression, as I was saying, is similar to linear regression, but now you have this Heaviside function. Remember, the gradient is very similar and the cost is very similar. The cost is very different, sorry, log likelihood, but the gradient is very similar. We have seen how we penalize. What we penalize is to try to beat the other value. So you have one. If you go to 0, we penalize a lot. We have seen this property of the CIMNE function. We have seen that the gradient is very similar to the linear regression and polynomial regression. We have seen that we are not going to use Newton. We're not going to use quasi-Newton. We're not going to use even gradient. We're going to use stochastic gradient. And we have seen that also regularization is very important, even for classification. Okay. So now in the afternoon, we are going to precisely compute one example of classification and use stochastic gradient and gradients and regularization. Okay.
Maybe it's similar to Ricardo's. So how can I know a priori error estimator of my classification or my regularization per se? How can I know if, for instance, in the example that we were working in yesterday, that we used the regularization to capture I think it was the first part well. How can I know that I'm well capturing or bad capturing the first part and that I need to regularize more, and where do I need to regularize more? Or even in the clustering here, how can I know that, let's say if you have the square and then you cut it in half, but maybe you are clustering well this part, the top left part, but not the bottom left part. How can I a priori known there is no
a priori? Yeah, you
a priori. I mean with my training. No, not
with training.
With the training itself.
With the training, just with information of the training, you will never know if you are doing well or not. You will know if you're doing well with the training. But if you don't put new data, you will not never know if you're predicting well.
So yeah, but is there any any level of knowing if it's, when is it called overfitting and when is it called underfitting? Is there like a way to measure this overfitting? And
yes, maybe I didn't explain this. So it was the last. Maybe we were doing it very fast yesterday, but you need to use the test. If you tell me you cannot use the test, I would say I cannot answer if we are overfitting or not. We are minimizing. We're not doing machine learning. We're minimizing. Are we doing well minimization? Is the cost small? Yes. Is the cost large? Yes. But if I want to know if my machine is doing well, I need to do the test.
okay.
And then if you start seeing that lambda increases and the test increases, you have to take the minimum value of this. And then is how you will know how well you are doing just with the test.
Maybe a reformulation of the answer of the question that I think that might extract more information is that there are methods that you can use all your data to train the model. For instance, cross-validation. Like you can use all your data in cross-validation and then extract test parts in each validation.
Yes, but you can do if you want. You can use all your data for training, but you have to do it many times, and one of the part of it should be test. So you can say, okay, I want to use all the data for training, okay, but to evaluate if I'm going to do it well, I'm not going to see how the train is doing. I always take this part. I will have 80% and 20%, and I will evaluate the test once with this splitting of the data. I will do it in another case with another splitting. I will use all the time all the data, but I will try to know at each case which is the error of the test, but always the test. This is very important to we try to internalize this idea because this is different from optimization. This is why it's different from optimization. We need the test.
So what I wanted really to know is if I could get a sense if my training data was good or not from this. Because in the example that we were working yesterday, for sure our training data was not good because it was very close on the left part, but on the right part, but on the left part I only had one data. But this is, how can I know from this, or how can I infer from this that I'm not gathering a well-trained, or that I'm not training my data with the correct data?
So, I mean, you will take the test and the train. So if both have similar accuracy and error, you are fitting you are correct. But if your train is really good and you see that the test is not at the same level as the train, you are overfitting, obviously. So you have to retrain it with more data or more parameters or whatever.
Is this line here? If you're here, you're satisfied. If not,
okay. Okay.
Okay. More questions? No. Okay, so let's do the lunch break and then we go to this classification.
Stop next.
Okay.